Welcome to this session. So now we go to see the topic elimination of function. So the function is of the form f of u comma v equal to 0. So whether the given problem is of the form f of u comma v equal to 0, if we can able to change, so v is equal to f of u or u is equal to f of v. So we can able to change this form to this or this to this. So now we enter the problem. So find the partial differential equation by eliminating the arbitrary function f from phi of x square plus y square plus z square comma x comma y comma z equal to 0. Therefore, this is of the form f of u comma v is equal to 0. So therefore, the given is phi of x square plus y square plus z square and comma x plus y plus z is equal to 0. This is of the form f of u comma v equal to 0. Here we taken this is u and this is our v. Therefore, u is equal to x square plus y square plus z square and v is equal to x plus y plus z. So this first derivative with respect to x and y we need in the further process. Therefore, we find here itself. So differentiating the function u with respect to x, we can get dou u by dou x is equal to, so 2x plus 2z into p. Similarly, differentiating v u with respect to y, we can get dou u by dou y is equal to 2y plus 2z cube. So again you go to differentiating v with respect to x and y. So dou v by dou x is equal to 1 plus p, and again v with respect to y, we can get dou v by dou y is equal to 1 plus p. So the required PDE is given by modulus of determinant of dou u by dou x, dou u by dou y, dou v by dou x, and dou v by dou y. So already these results we found already, so we can replace it here. So dou u by dou x is, instead of dou u by dou x, we can replace, so 2x plus 2z into p. Again, instead of dou u by dou y, we can replace 2 times of y plus 2 times of z into q. Similarly, we can replace dou v by dou x is equal to 1 plus p. So dou v by dou y is equal to 1 plus q. So since it is a 2 by 2 matrix, just if we take the determinant, so 2x plus 2z into p into q minus 1 plus p into this. Just we have to simplify this, we can get a solution. So two times of this. So multiple commonly bring out this yes to outside. So bring it to another side. We can get tends to 0 by 2 is 0. So again you have to multiple this x into 1, that is x. Similarly zp into 1. Therefore we can get zp. So again we can multiple x into q is this x cube. Again zp into q is zp cube. Again we can multiple this y with 1, so we can get y. Zq with 1, we can get zq. Again multiple y with this p, we can get yp. Zq with p, we can get zp cube. So now again we have to multiple this negative inner side. So write this x as it is, zp as it is, xq as it is, zpq as it is. So minus into plus is minus y minus zq minus yp minus zpq. So now we can cancel this zpq and negative zpq. So now we can club this x. So zp and yp. So then now this zp and yp commonly bring out the p outside. We can get z minus y into p plus. Again you have to club this x cube and this minus z cube. Commonly bring out the q outside. We can get x minus z. So now this x is there, minus y is there, then we can write x minus y. So here we commonly bring out the negative outside from this part, we can get y minus z. Here also we can bring the negative outside, we can get minus of z minus q. So we can write as it is. So y minus z into p, z minus x into q, that is equal to x minus y. So this is our required partial differential equations. So and also we eliminated our arbitrary function phi. So the next problem. So find the partial differential equation by eliminating the arbitrary function f from phi of z square minus xy, comma x by z equal to 0. Here also given is this. So this is of the form f of u comma v equal to 0. So here we can take an u is nothing but z square minus xy and v is equal to x by z. Similarly, we can find the first derivative u with respect to x and y, and also first derivative of v with respect to x and y. The required partial differential equation is determinant of dou u by dou x, dou u by dou y, dou v by dou x, and dou v by dou x. So replace the first derivative with respect to xy of the function uv. So we can get this. So here I can bring up by the properties of the determinant. Here 1 by z square is common in a row number 2. So I commonly bring it outside. So it's easily for can do the simplification. So that's why I have to bring it 1 by z square outside. Now we can take the determinant, multiple this and this, minus this and this. So we can get this. Simplify that one, we can get this partial differential equations, which is our required partial differential equations. So here we also eliminated our function phi. So next, so up to the last two problems we saw. So single function f or phi is given, so we can eliminate it directly. But now two functions are given, that is equal to f of y and phi of x plus y plus z. So therefore, we want to eliminate the two functions f and phi. So if it is a single function, it is easily we can able to eliminate in the first derivative itself. But in that more than one function is given, so maybe we need the up to second derivative we need. That means we want to find p, q, or s, t. So single function is there, we can find only p and q, or we can use in the form of f of u comma v equal to 0. So if the more than one function is given, we need to find the second derivatives, that is nothing but r, s, and t. So here given the first given equation, we taken as equation number 1. So z is equal to f of y plus phi of x plus y plus z. So partially differentiating with respect to x, we can get p is equal to phi dash of x plus y plus z into 1 plus p. Similarly, we can differentiating with respect to y, we can get q. So we can already we know that p is nothing but so dou z divided by dou x. Again, we go to differentiating this equation number 2 with respect to x, we can get so dou square z divided by dou x square. So that is denoted by r. Again, we differentiating with respect to y, we can get s, that is nothing but dou square z divided by dou x dou y. So in equation number 3 is nothing but so dou z divided by dou y. Again, you differentiating with respect to y, we can get t. So that is dou square z divided by dou y square. So we can get t. So with the help of PQRST, so here what it is given. So in R, so I bring this term phi dash of x plus y plus z into R. I bring it to another side, so we can get this part. So from these first two terms, I commonly bring out the one R outside. We can get 1 minus phi dash of x plus y plus z. So similarly, I do the same process in 5. So now I divided by 7. This taken as equation number 7. This we taken as equation number 8. So 7 by 8 we can get. So r divided by 1 minus phi dash of x plus y plus z whole divided by s into 1 minus phi dash of x plus y plus z. This one. So, and also this divided by this, the phi double dash and phi double dash get cancelled. So similarly, 1 minus phi dash of x plus y plus z, 1 minus phi dash of x plus y plus z get cancelled. So we can get this. Now we can now here also this 1 plus p the whole square, we can write 1 plus p into 1 plus p. So the numerator is square and this 1 plus p get cancelled. Therefore 1 plus p divided by 1 plus q. Just you cross multiple this, so we can get the partial differential equations. So that we can eliminate the arbitrary function phi and f, two functions. So we can eliminate it and get the partial differential equations. So the next problem here also we can, two functions are existing. So we want to eliminate the two functions. Therefore, as usual, what we did in the previous problem, the same case. So that is equal to f of x cube plus 2y plus g of x cube minus 2y. So partially differentiating the z with respect to x, we can get p. So similarly, we can get q with respect to y means q. So we can get r and t. So with the help of R and T, so just we have to simplify that, we can get a solution. As usual, the same process of the previous problem. Thank you.